I bet a lot of you out there are like me, fascinated by all the stuff happening with AI video generation. We're seeing these crazy short clips popping up everywhere. But what about creating like a whole minute of video with a real story, not just some random visual?
Yeah, totally. That's exactly the kind of cool stuff we're going to dig into today. There's this paper, right? It's called 1 Minute Video Generation with Test Time Training.
Okay, test time training. I like the sound of that already. But before we get too deep, remind me who's behind this research.
Oh, it's a pretty big deal, actually. A whole bunch of institutions collaborated on it. We're talking NVIDIA, Stanford, UCSD, even UC Berkeley, and UT Austin. So, not just some small group tinkering around. This is the real deal.
Serious brain power behind this. And it's not just theory. This is practical stuff, right?
Absolutely. They built this whole system, tested it out, compared it to other methods. The paper even got accepted to CVPR 2025. For those who don't know, that's like a huge conference in computer vision and AI.
Okay, so color me intrigued. What's the mission for our deep dive today? What are we trying to understand?
Well, first off, we're going to tackle the big problem these researchers were trying to solve. I mean, AI can make cool short videos, but why is it so hard to make longer ones that actually tell a story, right? And we'll get into their solution, those test time training layers we mentioned.
And of course, we got to talk about what this all means for the future, right? Like, where is AI video generation headed after this?
Exactly. And don't worry, we'll break it all down. So even if you're just starting to learn about AI and machine learning, you'll be able to follow along.
All right, let's do it. So we all see these AI-generated snippets, a few seconds long. What exactly makes it such a challenge to stretch that out to, say, a minute or even longer?
Right, good question. So a lot of today's best video generation models are based on these things called transformers. They use self-attention, which basically means they look at all the parts of the video and figure out how they connect to each other. The problem is, as your video gets longer, the cost of doing that self-attention just explodes. It increases quadratically with the length, which, it's not good.
Quadratic, huh? That sounds intense. Like, how much more difficult are we talking?
Oh, way more. Like, the paper gives this example. Imagine a 1 minute video. Once you break it down into those little units the AI understands, which are called tokens, you can easily get over 300,000 tokens. Now, if you were trying to do self-attention on that whole thing, generating that 1 minute video would take about 11 times longer than doing 23-second clips. Right. When it comes to training a model on that much data, it's like 12 times harder. It just gets way too expensive, way too fast.
Wow, 11 times longer just to generate? That's wild. So it seems like self-attention hits a wall pretty quickly when you want more than just a little snippet. What other approaches have people been trying for these longer videos?
Well, one big direction has been using RNNs, which stands for recurrent neural networks. These are designed to handle sequences, things that happen one after another, like a video. They kind of have a built-in memory of what they've seen so far. Some newer RNNs, like Mamba and DeltaNet, use a more efficient attention mechanism called linear attention. The computational cost grows linearly with the sequence length, which is much better than that quadratic explosion we talked about.
Linear, that sounds way more manageable.
Exactly.
So problem solved, right? Mamba and DeltaNet, are those the answer to generating minute-long stories?
Not quite. These RNN-based models are definitely good at handling long sequences, but here's the thing. The researchers in this paper found that they kind of struggle when the video has a more complex story, lots of scenes and stuff happening.
Yeah.
And they think the culprit is the hidden state.
Hidden state. Refresh my memory on that one.
Sure, it's basically the RNN's internal memory, right? It keeps track of what it has learned from the sequence so far. In traditional RNNs and these linear attention models, the hidden state is a matrix of numbers, and it has a fixed size. So now imagine you're trying to summarize everything important that happened in a long, complex video into this one little matrix. It's just not going to cut it. You're going to lose a lot of the details, especially the connections between things that happened way back in the beginning.
Makes sense. It's like trying to remember a whole season of your favorite show by just jotting down a few bullet points, right? You're going to miss all the good stuff. So we have standard transformers choking on long videos, and some RNNs can't handle the complexity of the story. What did these researchers come up with?
Okay, so this is where it gets really interesting. They introduced these new things called test time training layers, or TTT layers for short. These are still a type of recurrent layer, so they process the video step by step.
Okay.
But here's the kicker. Their hidden state isn't just a fixed size matrix. It's actually a small neural network itself, a 2-layer MLP to be precise.
Hold on, a neural network inside another neural network layer? That's getting pretty meta, isn't it? But I can see how that would give it a way more sophisticated memory.
Exactly. By having this neural network as the hidden state, it can learn and store way more information about what's happening in the video. It's a much more expressive kind of memory.
Okay, more powerful memory. I'm getting that. But what about this test time training part? What does that even mean?
This is where it gets really clever. Even while the model is generating a video, during what we call test time or inference, the weights of this little hidden neural network are being updated. And they're being updated using a self-supervised loss function.
Ah, self-supervised. That means the model is kind of learning from itself without needing us to explicitly label everything, right?
You got it. So it's like the model is constantly refining its understanding of the video it's creating based on what it's seeing so far. The researchers even compare it to how a model compresses a huge data set into its weights during training. Here, the TTT layer is kind of trying to compress the whole history of this particular video into the weights of its little neural network hidden state.
Huh. That's a pretty cool way to think about it. So what's this self-supervised task that's guiding the updates?
They use a learnable reconstruction task. Basically, they take a chunk of the video sequence, mess it up a bit using this thing called a low-rank projection, and then feed that messed up chunk into the hidden neural network. The network then has to learn to reconstruct the original clean chunk.
So it's like the network has to learn to fix what they broke, which forces it to really understand what's going on.
Yeah, you could say that. To make it even better, they actually have the network learn how to best mess up the input, which they represent with this set of parameters they call phi-k. And they also have it learn what the ideal reconstruction should look like, which is another set of parameters, pk. And then, since the messed up input has less information, they use another learned operation, vq, to project the network's output back to the right format. And remember, those key parameters are learned during the big initial training of the whole video generation network. But the weights of the hidden MLP, those are adjusted while the video is being generated.
Got it. So the initial training sets the stage for how the network should be adapting its memory on the fly. And you mentioned the hidden state is a 2-layer MLP. What are the important details there?
So this specific version, they call the TTT-MLP. It's a 2-layer MLP. And the first hidden layer is 4 times bigger than the input. They use something called GELU activation functions, which is pretty common in modern neural networks. And they use layer normalization to help keep the learning process stable. Oh, and they also have a residual connection, which is basically a shortcut that lets information flow through the network more easily, which is really helpful when you have deeper models.
Okay, so we have these TTT-MLP layers. They can adapt their memory on the fly. They sound pretty cool. But how did the researchers actually use them to build a system that can generate these longer videos?
Well, they started with an existing model called CogVideo X5B. This is a diffusion transformer model, and it was already pretty good at generating short clips, around 3 seconds long.
3 seconds? Yeah, that's not a lot of time to tell a story. So how did they take it from 3 seconds to a full minute?
So they took this CogVideo X model and modified it, right? They added their TTT layers, specifically those TTT MLPs, after each self-attention layer in the transformer. And here's the thing. These new TTT layers, they started with random values.
Random values? In a model that's already been trained, wouldn't that just mess everything up?
Yeah, that's a good point, and they definitely thought about that. To keep these new TTT layers from completely disrupting the pre-trained CogVideo X, they added this thing called a gating mechanism. Think of it like a set of switches that control how much influence the TTT layers have on the output. They start out really low, so the TTT layers don't have a huge impact at first, but then as the model learns more, they can gradually increase.
Clever. So it's like slowly introducing the new kid to the group, making sure they don't cause too much chaos right away. So these TTT layers start weak, and then become more important as the model learns. Now, diffusion models like CogVideo X are non-causal, which means they can look at the whole video sequence at once. But these TTT layers seem more sequential, like they process one step at a time. How does that work?
Right. To make the TTT layers work with a non-causal model, they used a technique called bidirectionality. Basically, they run the video sequence through the TTT layer forward in time, and then they also run it through backwards. By getting information from both directions, the TTT layer can effectively interact with the diffusion model. They call this bidirectional version TTT.
Makes sense. Got to get context from both before and after. And to keep things somewhat manageable, computationally speaking, they kept the original self-attention focused on those short 3-second segments, right?
Yep. That way, the self-attention can handle those local relationships within a segment, while the TTT layers can take care of the bigger picture, looking at the whole minute-long sequence and making sure it all fits together.
All right, architecture's all set. What kind of data did they use to train this new system to create these longer, more complex videos?
So they built this custom dataset of Tom and Jerry cartoons, about 7 hours of footage. But these weren't just random clips. They had human experts create really detailed storyboards for all of them. These storyboards focused on the complex, multi-scene stories with lots of action and movement. They chose this domain, Tom and Jerry, as a sort of test case, knowing that if they could make it work with this kind of content, it would likely translate well to other types of videos later on.
Tom and Jerry, huh? That's an interesting choice. Those cartoons definitely have some crazy storylines and visual gags. And you mentioned these detailed storyboards. What kind of information did those include?
So the storyboards were in what they called format 3, and it was really granular. For every little 3-second segment of the cartoon, you'd have a whole paragraph describing what's happening in the background, which characters are present, what they're doing, even stuff about the camera movements. It's a ton of detail, but that's important for teaching the model how to understand and generate these complex events.
And of course, they weren't just training on 3-second clips anymore, right? They were going for a whole minute.
Exactly. They used this multi-stage approach to gradually increase the length of the videos they were training on. They started with those 3-second segments just to get the model used to the style of Tom and Jerry.
Mm-hmm.
During this first phase, those TTT layers and their gating mechanisms, they got a higher learning rate, which means they learn faster.
And then they just kept increasing the length?
Yep. Over the next 4 stages, they trained on videos of 9 seconds, then 18, 30, and finally a full 63 seconds. But to make sure the model didn't forget what it had learned about video in general, they used a lower learning rate in these later stages. And they focused mostly on fine-tuning the TTT layers, the gates, and those original self-attention layers.
Makes sense. Building upon what it already knows, but also teaching it to handle those longer time frames. What about the visual quality, though? I mean, Tom and Jerry, it's pretty old, right? Not exactly high def.
Yeah, good point. To deal with that, they actually used a video super resolution model to upscale the original cartoons. That way, all the videos in their dataset had this consistent, decent resolution of 720 by 480.
Nice, so they spruced it up a bit. So we have the data, the architecture, the training plan. What about the prompts they used to guide the video generation? Did they always feed it those super detailed storyboards?
Yes. During both training and generation, the model always got that detailed storyboard format, that format 3. But they also played around with using less detailed prompts, like a short plot summary or a more detailed block, but without all the tiny details. They used a language model, Claude 3.7 Sonnet, to convert these less detailed prompts into that format 3 that the video generation model needed.
Interesting. So you could potentially just give it a basic idea and let the AI figure out the specifics. Now, for our more technically inclined listeners, any cool implementation details worth mentioning?
Absolutely. They had to get pretty creative to make this whole thing work efficiently. They were dealing with these long videos and constantly updating those hidden state weights, so parallelism was key. They came up with this strategy of updating the hidden state on small chunks of the video sequence at a time. These chunks are called inner loop mini batches. It basically lets them do a lot of the computation at the same time, which speeds things up.
And I bet this kind of thing requires some serious hardware, right?
Oh yeah, they were working with those NVIDIA Hopper GPUs. They really took advantage of this on-chip memory feature called DSMEM. To make their TTT MLP layers run smoothly, they use this technique called on-chip tensor parallelism. It basically splits the weights of the MLP's hidden state across the different processing units on the GPU. And the goal was to do as much of the calculation as possible within this fast on-chip memory to avoid having to move data back and forth to the main memory, which is much slower. They even built this custom software component called Thunder Kittens to make sure everything was as efficient as possible.
Sounds like they really optimized the heck out of it. So after all that work, all that optimization, how did their approach actually perform compared to other methods?
Okay, so they did a pretty thorough human evaluation. They used these pairwise preference tests, which means they showed people 2 videos generated from the same prompt, but made by different methods. Then they asked them to choose which video they liked better based on 4 things. How well it followed the text prompt, how natural the motion looked, the overall aesthetics, and how consistent the video was over time. And that last one, they adapted it to focus on things like smooth transitions between scenes and consistent perspectives.
Drumroll, please. Did TTT-MLP actually work better?
It did, by a pretty significant margin. On average, it beat all the other methods they compared it to. That included strong baselines like Mamba 2, Gated DeltaNet, and even some approaches using sliding windows of attention. It beat them by a whopping 34 ELO points.
34. That sounds like a lot. And put that into perspective for me.
Sure. So in the LMC's chatbot arena, where they evaluate large language models, a difference of 29 ELO points separates GPT-4o from GPT-4 Turbo. So yeah, 34 points in video generation is a big jump.
Wow. Impressive. Were there any specific areas where people noticed the biggest improvements with TTT MLP?
Yeah, the feedback showed that TTT MLP really shined in two areas. Temporal consistency, meaning smoother scene changes and keeping things consistent between different camera angles and the naturalness of the motion. If you check out figure 5 in the paper, you can see some visual examples. It's pretty striking.
So it really seems like that fancy memory system is helping it maintain coherence over longer periods. But you mentioned an evaluation with shorter videos, right? 18 seconds. What happened there?
That's interesting. In that shorter evaluation, Gated DeltaNet, one of those efficient sequence models, actually did the best. It even beat TTT-MLP slightly. So it seems like for shorter videos, maybe around 100,000 tokens, those RNN layers with the simpler matrix-based hidden states are still really effective. And they might even be more efficient in terms of how much computation they need.
So TTT-MLP is the champion for longer, more complex stories, but other approaches might still be competitive for shorter stuff. All right, every exciting new development has its limitations. What are the areas they're still working on?
Totally. The researchers were very upfront about some limitations. One of the main ones is efficiency. Even with all their optimizations, TTT-MLP still took longer to generate videos compared to some other methods. If you look at figure 6 in the paper, you can see the comparison.
So a trade-off between quality and speed for now. What else did they point out?
They also mentioned some visual artifacts in the 1-minute videos. Sometimes there were little inconsistencies at the boundaries between those 3-second segments, some unnatural movements, and stuff like inconsistent lighting. They think some of these artifacts might be coming from the pre-trained CogVideo X model itself, which wasn't perfect to begin with.
Got it. So maybe an even better base model could push the quality even further. What's next for this line of research? What are they hoping to achieve in the future?
They have a few really interesting directions they want to explore. First, they want to make TTT-MLP even faster, more efficient. They're going to keep working on those kernels and try to squeeze out as much performance as they can. Second, they want to figure out how to best integrate TTT layers into different video generation architectures. They specifically mentioned that autoregressive models might need different strategies than diffusion models.
And the big picture, what's the ultimate goal?
They believe this approach can be scaled up to generate much longer videos, potentially even hours long, while keeping the computational cost manageable. And their idea for doing that is to use even more powerful neural networks for the hidden state in those TTT layers. They even mentioned using a whole transformer network as the internal memory. Can you imagine that?
Whoa, a transformer inside a transformer. My brain's starting to hurt, but it sounds incredibly powerful.
Right. It could open up all kinds of possibilities for creating these epic AI-generated stories with consistent characters, plot lines, everything.
All right, let's wrap things up. What are the big takeaways for our listeners today?
The main takeaway is that these test-time training layers, with their super fancy neural network memory, are a huge leap forward in generating longer, more coherent videos, especially those with complex storylines. This is especially true for those longer videos. But it's also important to remember that there's a trade-off with efficiency right now. Some other methods might be faster, at least for shorter videos.
So the big aha moment here is that we might finally be breaking through that barrier of creating truly long, story-driven videos with AI. We're talking about a future where AI could make entire movies, potentially.
Exactly. And here's a question to leave you with. If a neural network can learn to change its own memory on the fly while creating a video, what other parts of AI models, which are usually fixed, can we make dynamic? Could we apply this test-time training idea to other types of data, like audio or text? Could we even use it to change the structure of the model itself as it's learning?
Now that's a thought-provoking question. If you're curious to see this research in action, head over to their project website at test-time-training.github.io, video-dit. They have sample videos, the code they used, even those detailed annotations. It's a fascinating look at the future of AI video generation.
Definitely worth checking out.
And with that, we'll wrap up this deep dive. Thanks for joining us, everyone.
See you next time.